Hello, it's Keith here, and today we're going to be doing a very simple beginner's episode on the ZX Spectrum. We're going to learn from absolute basics how to get Hello World written and compiled using just a single ASM file, and we're going to learn how to get it installed into a disk image and run it on an emulator as well. So if you've really got no experience and you want to get started, this should help you out. Now, I would recommend you download my development tools. They're available on my website, and they're what I'll be using today. But if you decide you don't want to use the assembler or the emulator that I use and my dev tools in general, I'm going to show you the things that I've used to get disk images, tape images, and TRD images working on Spectrums so that we can write our game and then run it and test it on the emulators. So let's have a look at the code we'll be using today. So we're going to be looking at two versions of a Hello World program today. The first is very simple. All it does is it prints Hello World onto the screen. The second one is a little bit more complicated, and it imports my monitor tools from my multi-platform tutorials. These allow us to see the state of the registers and also parts of the system memory, and this is useful if we're debugging our code. If we're writing very early code, for example a joystick routine or a simple graphics routine, it's not working as we expect. We need to be able to see what we're doing wrong. Are the registers what we expect them to be? Has our memory loaded into the correct place? So that's useful for that kind of thing. So that's why we're going to do that. But the first one is going to be just that very simple Hello World, and we'll be using the firmware to help us out and get things working as quickly as possible. So let's take a look at our code. We're going to be editing this in Notepad++ today, but you could use a regular Notepad or any text editor. This is just a text file, and we're going to compile it with Vasm. So the first line in our code is the command org hexadecimal 8000. In Vasm, the AND symbol represents a hexadecimal. So we're loading our code into 8000 in memory, which is 32768 in decimal. So that is the first position that the first byte of our program will be loaded into, and we need to know that later when we load and execute our program within the BASIC on the ZX Spectrum. Now the next thing we're going to do is we're going to load in the address of a string called message, and you can see it down here. So we're loading a pointer to this here, and we call this function called print string. Now we will have a look at print string later, but first I want to have a look at print char. Now of course a string is just a sequence of characters, so all we need to do to get this Hello World running on our system is create a piece of code that can print a character to the screen, and we're going to print whatever's in the accumulator. The way we do this on the ZX Spectrum is we need to open a channel. Now if I just run this program for a moment, just because I need to show you something, you can see here is the result of the program. You can see Hello World at the top here with just some random numbers here just as a test. I often change the numbers to check the compilation has worked correctly. And you can see at the bottom you've got another message here. Now these are considered two virtual screens. So this is the top screen and this is the bottom screen. And obviously the top screen uses 80% of the screen space, so that's what we want to write to. So we need to open a channel to the top screen. And the way we do this is we load the accumulator with 2. And then we call hexadecimal 1601, which opens the channel. Then we use an RST. This is a command that effectively calls a low address, and this will call the equivalent of hexadecimal 10 or 16. Some assemblers might call this RST2. It just depends on the terminology of your assembler. But this is effectively, on the ZX Spectrum, a print character command. On the Amstrad CPC and other systems it will be completely different, but on the ZX Spectrum it prints a character. Now, of course, the problem is we've used the accumulator just here, and so we've changed it, but we now need the accumulator to be correct so that we can print that character to the screen. So we're using push and pop here to back up our accumulator, which pushes it onto the stack and pulls it back again. You can also see we're pushing and popping a lot of other registers here, and that's because these commands actually change all of these registers, and for the proper functioning of our code, I'm relying on none of the registers changing during the print character routine. So if we wanted to just use this print character routine, we could just load the accumulator. So we could maybe do LD A comma apostrophe exclamation mark and then call print char. And you can see we've now got 2 exclamation marks here. We've added an extra exclamation mark at the end of the string with that print char command. So the print char command is very easy to use. But in this example, of course, we're actually using it as part of the print string command. Well, here's the print string command here, and it's common to all of these tutorials because this is a series. We've already done the Amstrad CPC, we're going to do the MSX and every other computer within my tutorial range as well. So the print string command is totally common. All it does is it loads in the accumulator from HL. It looks to see if we're at the end of the line, which is defined by 255, and if it is, then it returns. And then we increment HL, and then we will print the character that we read in here. So the accumulator was set here to the character in the string that's next. We call printchar to print it, and then we jump back to the top here and repeat again. But we're using HL each time, and that's why it's very important that printchar doesn't change HL. Now we could have protected HL here with a push and pop here, but it's more efficient to put it in the printchar routine, and it's also important for the monitor tools. Now one other bonus thing that I'm putting in here is a new line command. Now if we print the message twice, we would have it appear twice on the same line. You can see here, but that's going to get quite messy, and so if we're just doing little bits of testing, it's quite possible we'll need to start a new line to keep things nice and neat. So if we just do call new line in between these two, you can see we've now got two hello worlds on different lines. So we can use that new line command just to start a new line. Now the way we start a new line on the ZX Spectrum is very easy. We just print a character 13 to the screen. So we load A with 13 and then run the printchar routine. Now technically I could have just removed this line and it would have followed just straight into here, but I thought for clarity I'd put it in. The real purpose of that new line command is for the second example. Now here it is here. It's got a bit extra code here. We've got some more complex imports here, and we're not going to look at these. I've already covered them in my multi-platform series, but we're just going to run them today and see what they actually do. So here's the program running. You can see we've got our hello world messages before, but now we've got a list of letters and numbers here, and if you're familiar with the Z80, which I'm hoping you will be planning to become if you are not already familiar with it, we've got SP, AF, BC, DE, HL and PC, and these are various registers within the Z80, so we can see what those registers actually contain. And this is helpful if we've got a loop that is running more times than we expect. Well, maybe we need to check the BC loop counter just to see if it's actually decrementing as we expected. And then after that, we've got a memory dump. We're dumping the memory address 0, which is ROM on the Spectrum, and then we are going to show 32 bytes here, and we call monitor memdump direct to show those results. So if I change this to 4000, we'll be effectively showing part of the screen here, and you can see we're now showing just zeros. It would be showing the top line of the screen, I think, there. If we change it to 8000, we're now actually ironically showing our own code here. So this first part here would be this load HL common message here, effectively, and this CD is the call to print string just here. So 8028 is the memory address of the print string command, I guess. So you can see there that we're able to show bits of memory and register statuses. Now if you don't know what they're for, don't worry about it, because as I say, it's not the intention of this example to give you the full details of that. I have a full Z80 series if you want to see that. This is really if you know a little bit about what you're doing, and maybe you've programmed another system before, or you're learning your Z80 from somewhere else and you just want to get something running quickly on the ZX Spectrum. As I say, you can download my tutorial toolkit if you want, and I can show you here. We've got a lot of options for the Spectrum. We can load from a TRD image, which is a beta disk. And if I just press enter here, we're now loading from a disk image, and you can see that worked just fine. We can load from a Spectrum Plus 3 disk here. They're all very slightly different. And you can see that worked just fine. Or you can load from a tape image, which is what we were looking at just earlier. So we've got a lot of different options, but unfortunately creating these are quite tricky. Now we're going to look at the basics of creating these images right now. So how do we actually compile our code? Well, I'm using an assembler called Vasm, and Vasm comes with different syntax structures, and the one I'm using in my code is called old style. Other ones use different symbols. For example, for the hexadecimal marker I'm using an and symbol, and the position of labels and things might vary a little bit. But if you're using your own assembler, then hopefully a program as simple as this hello world won't be too difficult for you to convert. That said, I think Vasm's an excellent assembler, so I'd highly recommend you look at it. Anyway, when we use Vasm, I'm using a few standard commands like check labels, which just checks if a label looks suspiciously like the name of a command, which is usually if you've forgotten to put a tab in, like that for example, it would be mistaking push as a label. And I've got no case, so I'm turning case sensitivity off. I'm defining a few symbols, but you don't need to worry about that. This is For some of my code, I use defined symbols to identify what system I'm compiling for. The ones I really want to show you is the source file we're reading from, which you can see is %1 here because I'm loading this in a batch file, and the destination file, and I'm outputting to something called program.bin here. Now this is a temporary file because we need to do some work on it depending on the system we're going to compile for. Now this is common to all of the systems, so it doesn't matter if you're compiling to the 48K on a cassette tape, the +3 on a 3-inch disc, or the beta disc. So so our binary file is actually common in all cases. However, we do need to do some work to convert it. Now, if we're using a tape file, then we need to use a program called bintap. What this does is it converts a binary program into a tap file. Unfortunately, that only converts a single file, so we will be able to convert our program to a tape file, but we probably want some kind of loader file to actually start it up, a little basic program, and we're going to learn how to do that. But bintap is what we need. There's a link to it here, but it's of course in my download package that you can get from my website. Now, when we run bintap, we specify a source file, which is program.bin in this case, a destination tape, which I'm calling program.tap, a file name within the tape, and I'm using program C. The C is important, that tells it it's binary code. And then there's a loading address. Now, actually, I believe this loading address doesn't matter because this loading address in the file we ran today is incorrect. We're loading to 32768. The reason for that is the decimal version of hexadecimal 8000 here. So this 28672 is incorrect, but I think honestly it doesn't matter because we specify the loading address in our basic file later on. So that's what I use to convert my binary to a tape file. Once we've done that, we need to actually load our program somehow. And what I do is I create a little basic program. You've seen basically the same thing in all of these cases. If I run this one, for example, I've got it actually physically typed in here. And what I do is I save a memory snapshot and then load that memory snapshot with the emulator so that I can quickly start my program. But on the tapes, what I do is I put my program into a text file and then convert that to a tape. Now, the program is very simple in its essence, especially for the cassettes. All we do is we tell the operating system to load the next file on the cassette, and the next file is code, and to load it to memory address 32768. So that loads our program into memory address hexadecimal 8000. What we need to do next, though, is we need to call memory address 32768. Now, it's a bit odd the way the Spectrum does this. The command user is a user-defined function, and it says you run the function user-defined function at 32768. But these functions are designed to return some kind of parameter, a numeric parameter, and we need to do something with it. And the thing that everyone seems to do is to use it as a random seed. Now, the randomize command takes a number and just kind of changes the random number generation based on it. So there's no return of that value. And that seems to be what everyone does on the Spectrum for whatever reason. It certainly works, and I don't have any better ideas. So that's what everyone does. They use randomize user and then the address you want to call. So that's what we do. Now, this file we just save as regular text. And then what we need to do is we need to convert it to a tape file. And you use a program called mktap to do this. Now, I didn't write it, but I can't find the original. There's a very old version of version 1.0 floating around the internet, but I've got a very slightly later version. I've put it on my website, but as I say, I categorically can't take the credit for it. I didn't write it. But what it does is we can specify the name of a file. I've called it loader. We can specify a starting line. I've specified 10 here, which is probably the best, even though there isn't actually a line 10 in the program. It seems to work fine. A source file, which, as I've said, is text, and a destination file, which is, again, a single tap file. Notice we're using a different tap file in each case. Each tap file is only containing one file at the moment. So we've now got two tape files, and we need to combine them together. Well, in this case, we're going to use the Windows DOS copy command. We can specify copy, binary /b/y for yes, to disable any prompts. And then we specify the first file, which is our compiled basic file, as a tap, plus our second file, which is our code file, as a tap. That's here. And then a destination file, which is also a tap. And binary copy just copies the two files one after the other into one big file, and it seems that's what the ZX Spectrum wants, so that does us pretty well. So now we've got a file we can actually run, because the basic file will be at the start because we put it at the front here, and then our program code will be the second, and our basic file says load whatever's next into the memory address and run it. So as long as everything's in order, we will be just fine. And when we run Fuse, all we need to do is specify our machine. I'm specifying a 48K machine with the tape systems, and then we specify minus tape and the path to that tape that we just created. And I'm also doubling the screen size because why not? And that will get us a working tape, because that's basically what I'm doing today. You've just seen it run, that's how we create it. Now if we prefer to use the Spectrum Plus 3, the DSK file format, this Plus 3 was of course made by Amstrad, and the 3-inch discs were an Amstrad kind of thing. They didn't invent them, but they brought them in and they started using them. Now ironically, we can use the CPC Disk XP Amstrad program to copy our files onto the disk. However, unfortunately, the ZX Spectrum Plus 3 came after the Amstrad, and I think they came up with some new ideas for the header. The header's slightly different. So what I've done is I've created a little tool called Plus 3 Header. It's a C# program that you can download and run. All it does is it takes a binary file, it works out the checksum, and it creates a valid header for the file. And that will allow us to use our files with CPC Disk XP and create valid Spectrum disks. So Plus 3 header is very simple. All we do is we specify our source binary in the exact same way as we did before with the tape, and it's the same binary, no difference whether we save it onto a tape or a disk. We then specify a destination file name with the header, which needs to have a .c at the end. Notice it's a .c this time, not just a C here, slightly different. And then once we've created that file with a valid header, we just inject that file into our disk. Our disk is specified just here. We're adding it to that disk. And that's how we can add files to a disk image for the Plus 3. Now, once we've got our disk image ready, we actually want to run the code on it. Now, unlike before, we haven't created any kind of basic header. So what I tend to do is I load Fuse. I specify a Plus 3 machine, so we've got the BIOS we need and the disk hardware. Then I specify a Plus 3 disk, and I specify the file I created before here. And then I specify a snapshot. Now this is a memory snapshot, and it means I'm loading a save state of a machine. And the save state I load is the one you can see just here, and you saw it earlier. I've already typed a program in and it's ready to run. And the program is very similar to the one we saw earlier for the cassette machines, but there's just a slight difference. We're actually specifying a file name this time. We're loading into the same memory address. We're calling the memory address via the random user command. And I've just put a starting message just because I wanted to be able to see the program's really loading. And then I've just got run waiting to run here. So I just usually hit enter and that starts it up. And that will load our program and test it. Now, using a snapshot is great for testing because it means we're ready. You just hit enter and off we go. But if we actually want to create a disk for commercial release, we want it to automatically start without the user trying to work out what program to run or things like that. So all we can do is we can do save, specify the name disk with a K, and then type line 10, and what this does is it creates a file called disk which will automatically start from line 10, and the Plus 3 operating system will actually check for this name with its loader and it will automatically start the disk, and so we have a game that the user can very easily start up. So there we go. Now the Plus 3 disk is pretty good, but unfortunately very few of the Spectrums have it. The Plus 3 Spectrums weren't that popular, even the Plus 2s didn't have it, so very limited there. If we don't want to use cassette, our only remaining option is TRD beta disk. This was it's basically a relatively failed format back in the day. I don't think it really achieved much popularity, but it's kind of become the standard for emulation now. I've got a device called the Div MMC Enjoy, which is an SD card device, and it works absolutely superbly from beta disk, but it can't emulate Plus 3. So if you're looking to release on some kind of disk image, I think you really need to try and get TRD working, even though it's not very well documented. I've linked some documentation here that you can try out if you need to learn more about it. I'm going to teach you the very basics of it today, though. So, how do we use TRD? Well, we've got a thing called TRD Tool, and we can use this to add files to the disk image. I have to say I did have some trouble getting TRD Tool to create a valid disk image, so I've created a template image here and you can download it. And what I'd suggest you do if you're having to work with TRD is try and create the basic image within your emulator, save the image to your disk, and then use that as a template and just use TRD Tool for adding files to it. Now when it comes to adding a file to it, unfortunately TRD Tool won't overwrite an existing file. So what I always do is I have two lines in a batch file that creates these for me. The first line tries to delete the file. The second line adds the file to the disk. And this way, if the file doesn't exist, the first line just silently fails. If the file did exist, then it deletes it and re-adds it. And this allows me to update my disk image each time. It works very well. So you can see here we've got TRD Tool. The minus means delete. This is the disk image we're working on. And this is the file we want to delete. And then the second time we're adding, this is the disk image again, and this is the file we want to add. And this is the file in the same format as before. We just need to rename it to have .c at the end for the software to work okay. So that's how we create a valid TRD, just with the TRD tool to add the files for us and loading in a pre-created TRD image. How do we actually get it started? Well, once again, we need to specify the right machine. I use a 128K machine because the +3 machines probably won't have this. And then you need to specify Beta 128 hardware. You then need to specify the beta disk you just created just here, same file name. And again, I'm loading in a snapshot with the loading commands predefined. And boy, are they weird. Now, in the same way as when we did randomize user 32768 to run our program, the beta disk ROM has its own call address, 15619. Now, this just runs the firmware software, and then what that firmware software does is it looks at the rest of the line that called it and tries to find a command there. And to disable that command from being processed by BASIC, we put a rem in. So this rem is actually disabling the rest of the line, and the rest of the line says load program code 32768. So this is the command here being run by the beta disk hardware, which is being called by this line here. And we're doing exactly the same as before. If you look, it's basically the exact same thing as here, only this time it's being run by the beta disk firmware rather than the +3 firmware. So that loads our program into memory and calls it. Now, as well as randomize user 15619 to run individual commands, we can do randomize user 15616, and this will bring up a kind of DOS-like interface. Unfortunately, the commands are a bit weird, and I don't find it particularly easy, but if you want to learn how to use it, the documentation here is what you need to have a look at, because that will explain it. One thing I will warn you is if you use a very old version of TRDOS, they actually use different numbers. Some of the documentation you'll see will say other numbers other than 15616 and 15619. If you see that old documentation, it's obsolete. You want to find newer documentation, and if your hardware is using those older numbers, you want to try and update the firmware if you can. I mean, if you've got a real Spectrum with the real hardware, then I suppose you've got to work with it. But if you're using a ROM and your ROM is using other numbers, then you're using very old ROM, and you need to get something newer that uses 15616 and 15619, because the old stuff won't work anymore with modern software. So anyway, that's how we load our program here. Now, it's a bit of a pain, as I say. Once again, I save an image once I've got all this typed in, so that as soon as I run my emulator here, I'll just show you. So that's the first thing I see, because I've got a memory snapshot with this state saved, which saves me a lot of time. But of course, we can also create an automatic booting disk. We're going to do a save command via the beta disk firmware here. And what we're going to do is we're going to save a command called boot, which runs from line 10. Now, unfortunately, I don't think this actually works in all cases. It does work on my Div MMC Enjoy. I believe maybe it works on the Spectrum 48K firmware, but I don't think it works on the +2 firmware, at least in the emulators. But it's definitely worth doing, because it does work on the Div MMC Enjoy, and it makes it much easier to use the emulators for that. Anyway, this is how we can create our program and then put it onto disk images of all kinds. Now, I know all of this is pretty confusing. That's why I'm recommending you download my development tools. You just go to this link here and get dev tools, and you'll have all of the code here with all the emulators pre-configured, and hopefully you can just get things going really quickly. But I know some of you are quite enthusiastic to do things your own way, which is brilliant, and I just wanted to try and give you all of the information I've managed to get so far, and all of the tools I've managed to find that work well to get things working. And these are what I used to make the Chibi Akima's game for the Spectrum, and it seemed to go pretty well. Anyway, there we go. I hope you found this interesting. I hope you've learned something and enjoyed it. If you have, please like and subscribe. We're going to be doing lots of other systems, so maybe you'll find a new system you're interested in if you've previously only a Spectrum person. Thanks for watching today anyway, and goodbye.